Welcome to the Gravity Engine tutorial LaunchOrbit, which has been updated in Gravity Engine 9.2. But before we get into any of the details, let's just go ahead and press play and show in kind of rough terms what the scene will do for you. The goal of the scene is to launch a ship from the surface of the Earth into orbit. You use space to start the launch. And then you can press 1 through 5 to speed up the time evolution. So we'll press 4 here, and we can see there in the bottom left there's a bunch of parameters about the position, velocity, altitude, acceleration, and once the ship gets high enough, you start to see the inclination, apogee, and perigee of the orbit that's projected at the current time. And stages drop away, and then you can see here the fuel is counting down. We'll hit 5 and go a little faster, and then that fuel will count down to 0 and you'll end up in an orbit. And if you press function F1, you can now look at the green orbit of the ship that just launched and see it around the Earth. In this case, we had targeted an inclination of 58 degrees, and that was what was achieved by the launch controller. So let's stop all that and take it a step at a time. So let's begin with looking at the gravity engine component. So we'll click on the gravity engine component and look in the inspector. So the first thing to notice is that we've selected the XZ orbital plane. There's some information on the nbodyphysics.com website about left-handed, right-handed coordinate systems. If you want the ascending and descending nodes to look right in Unity's left-handed coordinate system, then you'd want to select the XZ orbital plane. The other thing is that we've picked orbital units, and that means that, as it's shown down here, our Unity units are 1 kilometer per Unity unit. We've also picked 3,600 game seconds per hour, so that's kind of 1-to-1 time, which is why we very frequently press the number keys to speed up the evolution time. If we now go on to the launch point, well, actually, first of all, we have an Earth, and the Earth has a sphere model, and the sphere model has been given a scale such that the diameter is the radius of the Earth. And we've also around the Earth put an ISS, and we've put a camera that gives us the Earth view when we press F1. So now we have a launch point, and one of the things that is new in 9.2 is this lat long point and the ability to control the launch point and locate it on the map. So here we've set a latitude of 28 and a longitude of -80, and that sets us up to be kind of roughly in the location of the Kennedy Space Center. And the other thing we do, if we look at this launch point, for example, if we look at the launcher, now go back to the launch point, what we have a choice of doing when we look at this launcher is, well, that's goofy. Why are you upside down? Okay, we'll stop there. Now let's take a look at some of the elements in the scene and how this all fits together. So we'll begin with gravity engine. So a couple of things to note. First of all, we have selected XZ orbital plane. That's to ensure that the ascending and descending nodes look correct in Unity's left-handed coordinate system. That's something you can read more about on a page I dedicated to that topic. We're using 1 Unity unit per kilometer, and we have also down here disabled the automatically add n body. And that's so that the n body that represents the rocket we're launching doesn't get automatically added to gravity engine and start falling through the Earth and trigger collisions and all that kind of stuff. Next, we'll look at the thing that's been added in 9.2, which is this launch point, and the component that it uses is called lat long point. And the purpose of this component is, given a latitude and a longitude, set the transform of this component and the rotation of this component. So it sets the transform based on the position of the latitude and longitude, and it sets the rotation of the component such that it is perpendicular either to the center of the Earth or to the mesh that it finds itself sitting upon. The model we use for the Earth, if we go up to the Earth here and look at the sphere that's representing the Earth, so it has a diameter that is the Earth diameter in kilometers, and it also has a mesh collider that is marked as not convex. And the launch point will use this mesh collider and project a radial line from the requested latitude and longitude until it finds the triangle on the mesh that shows the graphical representation of the Earth's surface. Now, this won't actually be at the Earth's radius because these triangles approximate the Earth's radius, but except at vertexes, they're never exactly the Earth radius. And you can see that the lat long point at the bottom here says offset from true radius minus 48 kilometers and normal angle error 3.38 degrees. What that's saying is that in order to make the launch point appear on the surface of the sphere model, we have to actually be 48 kilometers less than the nominal radius of the Earth. Now, you can turn this off if you wish. So if you turn this off, then what you'll find is that the launch tower jumps away from the surface. And if we zoom out and look around a little bit, you can see that it is in fact floating way above the mesh of the surface. And if we click raycast to surface again, it snaps us back down to the surface of the Earth where we want to be. Notice that the spaceship is a child of the launch point, so it inherits the position of the launch point, and it inherits the orientation of the launch point, so it appears locally vertical to the piece of the triangle mesh that we're on. As soon as we hit launch, if we use a launch controller, it will automatically start to steer the spaceship based on the actual true radial direction. So you may see a slight deviation in the angle of the rocket once launch is pressed, and that's the reason. Now let's take a look at the spaceship and the way it's handled in the scene. So we have a spaceship component, and when we look at that, we see that it has an end body, and the mass of this end body is 0. For the purposes of gravity engine, since the Earth is 10 to the 24 kilograms, it's basically the mass of the spaceship is 0 as far as gravity is concerned. For the rocket engine calculations, we will actually make use of a real mass for the spaceship. In addition to having this end body script, it has a script attached called Earth Rocket. And Earth Rocket is the way in which the normal gravitational evolution of the ship is influenced by both the rocket engine and the atmosphere. So let's pop into that script just for a second. And so here it is in the left pane here, and you can see that the Earth Rocket implements an interface called GE external acceleration. And when objects with this interface are added to Gravity Engine, it hooks into the main integrator loop and calls out to a method called acceleration, which asks the implementing class of the interface to perform an acceleration calculation so that if there is some external acceleration influencing the object, such as a rocket engine or atmospheric drag, it can be included in the numerical evolution at the same time as it's adding up the various gravitational forces. So what this Earth Rocket does is it basically delegates to two separate components. There's an engine, which is a multi-stage engine, and there's an Earth atmosphere model which provides the drag based on the altitude above the surface of the Earth and the air density. So if we go back to Unity, we can see that under the spaceship we have a spaceship model, we have a camera, we have the rocket engine, which is where our multi-stage engine lives. This is a script that allows you to specify a number of stages and give the mass of the payload and then the empty mass of each stage, mass of fuel, burn rate, thrust, and also items needed for the atmospheric drag calculation, which are the cross-sectional area and the drag coefficient. It also allows you to include an effect object like a rocket flame particle system, which will get started as things go forward. Now let's take a look at how the scene is controlled. So we'll go to the launch controller component, and there are a couple of items added here. There's a launch user interface, there's a launch controller, there's ship info, which provides the on-screen information about position, time, fuel, acceleration, and so forth. And there's also a time zoom script, which allows us to use the number keys to speed up the evolution of the scene. Notice with the launch UI, there's a couple of comments here: F1, F2 for camera select, space to launch, WASD to steer. Now the steering will apply only if the launch controller is disabled. The purpose of the launch controller is to actually do the steering for you. So if you want to steer manually, you want to either remove or disable the launch controller script. The launch controller script allows you to set a target inclination of the orbit you want to reach. This inclination must be equal to or greater than the absolute value of the latitude you're launching from. That's just an orbital mechanics thing. You can't be north of the equator and launch directly into an equatorial orbit without some kind of correction burn. And this controller won't handle that for you. It just puts you directly into an orbit. It also allows you to set a time range for a couple of curves that are useful for controlling the ship. So here we know that the rocket's going to burn for about 500 seconds, so we set the time range to 500. And then we have a pitch curve, which allows us to control the pitch of the rocket. So we start off pitched at 90 degrees, so we fly straight up through the atmosphere, and then we curve so that we're tangent to the orbital plane that we want to be in. Similarly, there's a thrust curve, which has a small dip as to sort of mimic the kind of things that happen when you want to throttle down for maximum dynamic pressure, and you can edit these curves in the usual way. And the controller script will take values for pitch and thrust from these curves as things go on. There's one other useful function that the Launch UI script provides, which is related to the camera select function. So the scale of the ship is somewhat exaggerated when it's sitting on the ground. It ends up being a kilometer or two long. This is one of the classic problems of space games, is that the gravitational scale and the model scale are usually fairly incompatible. And it isn't always easy to do one for one in Unity coordinates, although if you want to work with really small scale numbers, you can do that. I chose not to do that. And the thing that this script will do is, as you flip between the ship view and the Earth orbit view, various items in the scene will get automatically scaled. And that happens in this Launch UI script, so we can just pop in there and have a quick look. And what you'll see is that it makes use of these constants, which have a different scale for the ship when we're using the camera looking at the entire Earth than we do if we're using the ship view camera. And also the scale of the line renderers that show the orbital paths are adjusted depending on which camera you're using. And this is the kind of thing you'll quite often need in a space game where you're jumping between a kind of local ship view and a faraway see planets and moons kind of view. So at this point, we can just demonstrate all of that once more by hitting space. Sorry, playing the scene first. Hitting space, so our rocket does tilt a little bit as we go to the true normal and not just the normal of the surface. We'll speed things up here by pressing 4. We'll start to climb up. We're targeting an inclination of 58 degrees. As soon as we get above, I think it's 50 kilometers, we start turning on the orbit predictors and trajectory prediction. And if we press F1, we can now, and use the arrow keys to turn around, we can now see the projected orbit as we take off. And as we apply more thrust, that orbit will turn from a path that collides with the Earth to one that is actually a true orbit around the Earth. You can see here we're headed off into a 58-degree inclination. We've now got to the point where we're in a full orbit. We've got engine shut down, and we're in our orbit at 58 degrees. Thanks for your attention, and hopefully this scene gives you some fundamentals to start to use Gravity Engine in whatever your project is. Thank you.